Hi everyone. My name is Jonas Bonnier. I'm from a small startup called Scalable Solutions. We're the company we have a lot of committers working on Akka. I started Akka about 2.5, 3 years ago. I started thinking about it at least, and then I released the first version of it about 1.5 years ago, and after that it's just grown. Now it's very much a team effort, and I'm really glad to have Gary Evans with me here today. He's an Akka committer. He started using Akka at his company, writing a sort of data, compute grid style work queuing, work scheduler system that he's going to talk about later in this talk. I'm going to first give the first 30 minutes to give an introduction to Akka, and then Gary's going to show us a little bit how it can be used, more like war stories, how he's using it in the real world. So that's really exciting for me as well. Taking a step back, why I created Akka, I started and why we are doing it. We have a Debasis Gosh here as well. He's also an Akka committer, so you can grab either of us afterwards if you have questions, if we don't have time to answer all of them or so. So taking a step back, I think the common theme throughout my career has been way too hard to write highly concurrent systems, highly transactional systems that doesn't crash or starting to be problematic under heavy load. Writing truly scalable systems using state-of-the-art tools, and it is a problem that is getting more and more attention now. I mean, we have this multi-core crisis. We need to scale both up and out and all that. And so Akka is sort of an attempt to solve this problem. And the vision with Akka is to give you simpler concurrency, simpler scalability, and simpler fault tolerance using one single unified programming model and one runtime service. And Akka is more of a toolkit than a toolbox, you can say, rather than a framework. It's very modular. It does a whole bunch of stuff, but Akka actor.jar, for example, the essence, the core of Akka, in the upcoming release coming in next week, we have 0 dependencies. So it's very, very lightweight. It's used even on Android and so on. Hey. But it does a whole bunch more, and you can bring in more pieces along the way. So it will try to help you to manage system overload, basically. It's a unified way of scaling both up, meaning using multi-core processors. Some years ago, people were mainly talking about scaling up by buying a very expensive Sun 32-way box, for example, for some millions. But the last 10 years, commodity hardware is becoming really cheap. So then people started scaling out, utilizing many of these machines. But now, since we have this multi-core crisis, all this, it takes more than one clock cycle to reach the whole chip. We can't get any bigger chips. We need to get more chips. Then we're back to scaling up. So we need something that can take care of both. And Akka tries to do that in a unified way. Basically, it's configuration option if it should be scaled up or scaled out. Replication and distribution for fault tolerance, also things like transparent load balancing and so on. These are all things that Akka can help you with. Okay, the architecture is that this is sort of the essence of Akka. It gives you fault tolerance, scalability, and concurrency, and it has more than actors as a concurrency paradigm. I like it, or I say as a concurrency tool. It has also software transactional memory. It has agents. It's also a data flow concurrency. But we're going to focus on actors in this talk, since it's it's the cornerstone of Akka. But actors doesn't solve all problems. There are certain kind of problems that are impossible to solve using actors, and then you need other abstractions. So, but there's also much more to Akka. It has a whole bunch of different modules So they can bring in whenever you need whenever you need stuff. I think Gary's going to talk about some of them today. He's been involved in the HTTP module, for example, doing some very cool stuff there. It also has some enterprise sort of features if you're interested in monitoring management and provisioning and stuff like that. Just short, where is Akka deployed today? We see deployments in finance, and stock trend analysis, simulation, event-driven messaging systems, betting and gaming, as well as telecom and other areas as well. All of a common theme throughout all these are like highly transactional, highly throughput systems, low latency, and with like really high need for availability, systems that can't go down. So first, some theory then. What is an actor? How many ever heard about actors in the sense of not like Brad Pitt or stuff, but in the sense of software engineering? Actor is really nothing new. It was defined in the thesis by Carl Hewitt, 73, I think it was. It was embraced and sort of popularized by Erlang starting in 84, I think. Pardon me? 87, but they started working on it in 84. I'm pretty confident. Okay, yeah, okay. But it's still old. It's nothing new, but it's gotten sort of a revival the last years, and Akka embraces that. So what is an actor? It's basically an object. It has state and behavior, and the difference from like a classical object in the Java sense is that it has a mailbox, this little thing here, in which messages comes in order, and an actor can only take one message at a time. Okay, an actor is also sort of, they can be thread based, but most actor systems are event based. That means the actor are reactive. They are extremely cheap. They are only bound to memory in terms of resources. So they run on sort of an event-based thread. How it really works is that there is a scheduler that can take actor from a pool and resume it, have it run on a real operating system thread for a time slice, and once it's like time's up, then it's passivated, suspended, and put back. So, and another actor can run on that thread. So they share sort of time slice on a thread pool or a number of thread pools. So they are event based. They only act when told. So they work like reactively, lazily. And so if this actor now it's their turn to run, it will take the one message out of the mailbox, it will process it, and while it's processing it, other messages can be added to this mailbox. But the actor model is that an actor can only process one message at a time. Okay, so and each actor is by essence single-threaded. So you get concurrency by running many actors. And an actor in Akka is about 600 bytes. So on 8 gig of RAM, as I have on this box here, I can run around 13 million actors. And that is not a problem, because they only consume memory. Okay. So actors are actually closer to Alan Kay's original definition of object orientation than classes in Java. It can be something to think about. So you can really think about them and model them as OO. Okay. Actors in Akka. Akka has a Java and a Scala API. So the Scala API is a little bit slicker, a little bit less verbose. You can do exactly the same thing in Java. It looks almost the same, but not exactly, but almost. But I will throughout this presentation, I'm going to only talk about the Scala API. Okay. So to create an actor, I extend the actor trait in this case. In Java, it is a base class. And I only need to do one thing, and that is required, and that is to implement the receive method. The receive method implements my message handler, basically defining the behavior that the actor should have when a message of a specific type has arrived and is like being taken from the mailbox and put into the actor. Okay, this little actor is a counter. I also need, alongside with the actor, I also need to define the message or the messages that the actor can respond to. An actor can respond to one or many messages. Okay, and that is sort of the public API to the actor. So if I now implement this receive method in the Scala API, it uses pattern matching to be able to match on the messages that come in. So here I say, okay, if it is case of tick, meaning if it is a tick message that just arrived in my mailbox and I'm being scheduled, then I run this handler. In this case, I'm just incrementing the counter. The actors are completely thread safe. You don't need to use any like atomic longs here or volatile vars or whatever. Okay, they are sort of the abstract away concurrency through the actor model that is enforced by the runtime. So, and what is nice is that it raises the abstraction level from being, thinking about the plumbing, the locks, and release locks, take locks, wait, notify, wake up things here and there. All of that just vanishes, and instead becomes workflow. Okay, so the concurrency is lifted to the workflow level. How do my components interact with each other? Okay, and it's very, very highly optimized how the concurrency is done. In the critical path, there's only one single volatile write, so it's extremely optimized. Okay, you create actors using this actor of method, and out here comes an actor reference. It's not an instance to the actual running to the actual like new actor object, the counter in this case, but it is a reference to the counter. And this level of indirection is great for many reasons. First, it's less likely that you will shoot yourself in the foot by adding public methods to the actor, meaning that if you call those, you go outside the actor model and you will get into race conditions and all that kind of problems. Okay. It also are things like these references are location aware. So yeah, I can take one of these and send it off to another machine, and it will remember which actor on which machine it is representing, and just work. Okay, so it also abstracts away not only concurrency but also distribution. They are sort of location transparent, you can say. And that is sort of the why actors are so great for scaling, basically, because they are really embracing sort of distributed computing in a complete transparent fashion, which is slick. Actors, they can be started using the start method. It can be stopped, and that is basically the life cycle. Then they can be restarted upon failure, but that is something else I'm going to talk about later if we have time. You send messages using the bang operator, and that is an asynchronous message send. So this method, this is actually a method call. In Java, it's called counter.send one way and pass in. And you can use that from Scala as well. But we have taken the Erlang style of method naming, because like this bang operator is the common way of sending messages in Erlang, and that is what most people are used to if they used actors before. So this means sending the tick message to the counter actor, and that only means putting it on his mailbox, and that is guaranteed. It's guaranteed to end up on his mailbox in order. But after that, the method returns. So it's asynchronously then it's asynchronously eventually going to be scheduled to process that message. Okay, I will not wait for it to do that. Okay. We also have the triple bang method. Actually, we're going to rename these methods for Scala for Akka 2.0. This one is going to be renamed to question mark, because it's really a question. You ask something and you get a reply. What this does is that it will send a future what it will do, it will immediately return a future, and it will allow the actor that receives the message to resolve that future asynchronously. Okay? So this thing returns immediately, and I can wait on it whenever I want. I can choose to do it right away and retrieve the result, but I can also choose to not do it here, because this await thing is blocking. Okay? When I do say await, then I actually block, and blocking is bad. It impedes progress. It has very high impact on throughput. I mean, we've done some benchmarks, and it's basically something that you should avoid as long as possible. We have a lot of interesting methods that allows you to do composition on futures and work with futures without blocking, and block as late as possible. So you can even create your own futures, but in most of the cases, if you use these methods to send messages, then the futures will be created for you. You can also create them and pass them around, and they are much richer than the Java usual concurrent future that you might have seen. That is a. Yeah, but they are not callbacks. Callbacks are bad, right? Because I mean, especially in a language that support closures, because you can actually bring with you the context and update that concurrently in two different threads, and then you're back to share state concurrency. But this is a safe way of doing it, and sometimes it's very convenient to have this request reply idiom. I try to avoid it as much as possible, honestly, but it's there for convenience. But we have a lot of nice methods on the future that allows non-blocking composition of futures. So you can actually delay the blocking wait as long as possible. Okay. We'll, for example, have the onComplete that will never block. It will only you can register callback that will run in the same thread as you receive the future. You don't need to worry anything about you will get into any race conditions or anything. We also have high order like combinators, right? So like reduce and fold and so on. So you can take a whole bunch of futures. You can process them in a non-blocking fashion and then get a result back. So you can do all kinds of things like that. We also have the bang bang operator that will use a future under the hood, but it will block. So this looks like a regular synchronous method dispatch, but it's not. Okay. We can also have this reply method that allows you to, once you get a message, say reply passing in a reply, and what's going to happen then is that will be sent back to the guy that sent me the message. So the sender address is implicitly passed along with the message, even across machines. So you can just say reply, it will end up with the guy that just sent me the message. Okay. Actors also allow you to redefine the behavior at runtime. So you can actually swap the actor's implementation or message handler at runtime using the become method. And that sounds a bit funky, and why is that useful? This actually turns out to be useful in many practical situations. I use that all the time when I want to implement like state machines, for example. Often actors are state machines, and now you can sort of go from one state to another by redefining the messages that I can accept in this state. And when I change my state, I can go back to another set of messages that I can reply to. It also allows you to actually do things like upgrading the behavior at runtime in remote actors, and you can all do all kinds of interesting things there. You can also do unbecome. Here is how you can send a HotSwap message to an actor to change it from the outside, while become does it from the inside. I can become something else myself. You can also do unbecome and send an unbecome HotSwap message as well to have the act. And you can also define configurably if you want to have that as a binary property, or if you want to have a stack of behaviors and append to the stack and pop the stack. Okay. Akka also sort of breaks apart the actor implementation from its scheduler. So the scheduler is something that you configure from the outside. It's very highly configurable. You can set different dispatchers. We, for example, have the regular dispatcher is great. The default dispatcher is great for many situations, but we have some other more targeted dispatchers. For example, a work stealing dispatcher that allows you to create a whole bunch of actors with the same type, have them share the work stealing dispatcher, and off they go. And if one actor runs out of messages in his mailbox, he'll try to steal from the other ones, and so on. So that is scaling up. Scaling out, remote actors. As I said, actors are great for scaling out as well, embracing distributed computing. In Akka 1.0, we, up to Akka 1.0, or actually Akka 1.01 that's going to come next week, or the first RC is going to come next week, we've had something called remote actors. We have client-managed actors and server-managed actors, in the sense that the client manages the life cycle, can start up actors on remote machines and shut them down. Bad in an untrusted environment, where server-managed actors are greater, in which the server manages the life cycle. So you register a server-managed actor and expose basically a handle or an address in which other clients can talk to that. The problem with this approach, it's been pretty successful. I mean, I've used it in a whole bunch of production systems and so on, but the problem is that deployment, basically defining if it should be local or remote, is a development decision. You need to say, oh, now create a remote actor, now create a local actor. You also need to hard code the topology by saying, okay, I want to look that actor up on that machine over there, on that port, and so on. And we don't want that, really. We want to be able to change that dynamically and adaptively, so it needs to be a runtime decision. And that is what I'm working on right now. Coming in the upcoming Akka 2.0, hopefully released in the summer, is to move away from that. Okay? So instead, we're introducing a concept of address. This is work in progress, so I want your feedback as well. But the idea is that you can set an address to an actor, and that's sort of a virtual address, and that is sort of separated from how it should run eventually later. Okay? So it's decoupled from the actor is completely decoupled from how it should be deployed. So if no configuration exists, then everything will just be local actors. Okay, so it's very easy for development. You can run it within your IDE or whatever. But the option is that when you run it, you can write a configuration for how it should be deployed. Okay, and then the exact same system, no code change, can be configured to run in a distributed environment, saying that this actor should be running on these 3 machines, it should be load balanced using that algorithm, it should be replicated, all these things. It's now a deployment decision, yes?
Deployment of the server cluster or deployment of the client? I mean, what's initiating the actor?
Deployment of this actual code that you're running. So if you've written a server, like a network server, for example, when you, for example, run that in Amazon, you can just, then you configure it then you deploy it and tell it how it should be configured and communicate between each other.
So it conceptually just has a...
So for the client, it will look the same. That is the point. Yeah. Okay, so this is what we've had right now. As I said, it's up for feedback, but now we can say that we had this service, my service. If we don't have a configuration, it will just run as a local actor. But now, if we pass in a configuration like this when we boot up the system, then we can say that my service should actually not be a local actor, it should be a clustered actor. Its home address should be here. So it will be deployed onto that machine. It should be, everyone that sort of gets a reference to it will get that through a router, and using, in this case, the router least CPU, so it will just redirect every message to the system that has the least CPU. We have a whole bunch of different routers, like random, round robin, least CPU, least memory, least messages in the mailbox, basically work stealing, and so on. You can say if it should be stateless or not. Yes?
So this is an external configuration?
Yes?
Not an internal ESL?
It is you put this in the standard Akka.conf configuration file, but we also have a programmatic API in Scala if you prefer. But the whole idea is that it should be completely outside the development of your system. It should be configured outside somehow. Okay.
Okay, thank you. What's the refer to?
Pardon me?
Open represents the address for the router, or
For the actor.
for the act? Okay, so you could have a list of those.
Yeah. This just gives you, I mean, there's a lot more to it than this. It just gives you a brief idea where we want to head. So you can choose if it's going to be cluster or local, of course. I mean, you can say it should be stateful or stateless. Stateless actors are extremely simple to scale out. I can even have the system adaptively create new actors on other machines and using the elasticity on EC2, for example. Stateful actors are harder. Then the replicas will mean basically creating identical replicas and do replication between them for failover, in which you need one master naturally and the other ones as backup, and so on.
What's the feedback mechanism that you use with clustered actors to figure out how you scale it up or down, right? So I see that you can distribute it.
Yeah. We're using Zookeeper as a coordination service, and we gather metrics. We have in the monitoring management, we have a Dapper style metrics gathering similar to the Dapper paper in Google, in which we can like annotate messages with metadata, so we can trace them across machines, and we can see exactly what's going on in the system. Since all of that is in one single central intelligence, we have all options, everything we need to do these things. Basically, currently we're working on tight EC2 integration to take advantage of the elasticity in EC2. So actually, not only spawn up a new actor on another machine on existing host, but also spawning up a completely new machine and move actors over there. And so on, and shrink. So this is what the runtime currently provides. Subscription-based membership, and we have a highly available cluster registry for looking up actors. We do replication. As I said, we do all kinds of stuff. I don't even want to read all this. You can get the slides later. Leader election and compute grid stuff and so on. So just, I have 5 more minutes, or yeah. I don't want to steal too much of his time, of Garrick's time, but I just want to say some words on the third thing. Now we have talked about actors for scaling up, scaling out, but actors are also great for fault tolerance. Okay? Here we adopt the Erlang model. This was actually the reason why I got interested in actors in the first place. Read about this mythical 9 nines availability. I thought these guys were lying. Then I looked more into it, and I understand that it's alien technology. But that's actually not true, because that's Lisp. So I don't really know what these guys are using. No, kidding aside, it is a true story. They used Erlang naturally at Ericsson, then to write a telecom switch, in which they achieved 9 nines availability. I mean, I've been working with these things. I used to work at Terracotta, BA Systems, and so on, writing these things for a living. And 5 nines is really, really hard. 9 nines is, yeah, I don't know. It's almost impossible. But they used a model that's very different from what we use in the Java enterprise in general. A model also known as let it crash. Basically have a system watch itself and repair itself at runtime. So I felt that I need to dig into this. I learned Erlang. I tried to convince my clients and my colleagues to everyone must learn Erlang. No one wanted to do that because they were all in JVM. So I felt I need to implement this myself, and I started Akka. That's basically long story short. So what is this all about? If we take a standard O application, it might look something like this. And if we now look at all the objects or components that has explicit error handling, guarding critical data, it can usually look something like this. It's usually scattered all over the place. Usually even guarded with try-catch here, try-catch, and try to repair itself all over the place. It's just a big mess, okay? So now if we would first try to classify the state, we can have scratch data. That is really easy. That's data used during computations. We can have static data. I mean, easy in terms of failover. Just throw it away. Static data, supplied at boot time, supplied by other components. Usually you can look that up. It's also pretty easy to deal with in a fault-tolerant situation. Dynamic data is harder, especially input from other sources than you have control over. User input from external systems. That is the really, really hard thing. And that needs to be protected by any means because you can't possibly recreate that data, okay? In the actor-based systems, you usually tend to write your system as a fault-tolerant like Onion. And you talk about something called the error kernel, okay? So the error kernel is where you put all these critical data. And then you add like first, second, third, fourth level of defense, like an Onion. And the basic idea is as soon as you are about to do something dangerous, you never do that yourself. You delegate. You delegate to someone that is okay if he dies. You spawn up a worker. If he dies, it's fine. Because I'm fine. Okay. So if something comes in here and my worker over there dies, right? What's going to happen then is I'm going to get a notification in the higher level, okay, in the higher layer. And what I do is I declaratively configure my system to act upon failure. So if that happens, I've already configured my system to deal with that by restarting the system, the component to a stable state, okay? If this guy dies over here, I might have configured him to actually to be sort of be part of a group of actors, because it might be the actors are implicitly coupled, and just killing one of them might not help because they are sort of working together to do something. It's really nice to have this invariant, this binary property that either know that either all actors in this subsection of the tree is dead or all are alive. There are no zombies, nothing in between. It might actually be that if this guy dies, then this actor here doesn't have the power actually to do something about that. What's going to happen then is that he will also kill himself, and the error will be propagated up. And hopefully, the error is not so severe that I can't handle it. If it's out of memory, it will hit the error kernel. The whole machine will go down. But that's very unlikely. Very likely that you will be able to have an error that actually is repairable, so the system can repair itself. And what's nice is that you can be as coarse-grained or as fine-grained as you want. Okay. So it's about sort of letting the control over the fault tolerance go. Delegate to someone else. I just die. Someone else deals with the problem. Okay. If you want to build a fault tolerance system, you can never just write the system with just a single box, because you can get a hardware failure, you can get out of memory, right? But linking also works across machines. So you can boot up a system linking across machines and have one system watch another, or one node watch another node. So if this node goes down, he can hopefully repair himself. If it propagates all the way up here, he will eventually find out here. And he can then choose to start up that actor branch on another machine, for example, and so on. It's much, much more. So now I'm going to hand over to Garrick. He's going to talk about some of these. HTTP, for example, but there's SDM, there's a finished state machine module for those like that. JTA, we have a mini app server, microkernel if you like that. If you're into Spring or Juice, we have support for that, and so on. And Akka is very modular. All these are modules. Just bring in what you need. So.
Thanks. So my name is Garrick Evans. I'm a software architect at Autodesk, and I run architecture and research for an emerging technology group. So what I want to talk about is this project that I've been working on for about a year or so, started out as a prototype and is now kind of reached production status called Hydrogen. So this is what it's supposed to do. This is what I was asked to worry about a year ago. It's a pretty big thing. But the general idea is that we would be developing services either for our existing products or new web services to be put out there, trying to leverage a lot of the IP that we already have in the company. And the stuff on the bottom here is what this grid is supposed to do. Your typical stuff in terms of providing applications or services, trying to deal with partitioning, either to provide different levels of functional service or quality of service. It's supposed to scale out not only in Amazon, but in our own data centers. And then we have these gray areas, or kind of these feedback loops, where information, say from business models driving offerings of how do we want to create new ways of either directing customers to new services or offering more granular units of work. A lot of, say, very expensive simulation licenses are, it's like 25 grand or something for the license, but and a lot of people who want to use the software can't do that. So they might put something together which is hourly rates or something like that. And then we would be collecting data through sort of semantic events, introducing metering and quotas, and then also then using a sort of a longer term processing for analytics, operational audits, those kinds of things. So these are some examples of services that are out there today on our lab site. I invite you to go and take a look at them. But we use varying degrees of the system for some of these. So rendering, design optimization, and some general work, which these tend to fall into categories of you have a big bunch of data, you can configure your jobs, you fan them out, you fan them back in, you process the results and make them available to the client. So this is, that's your typical Autodesk software engineer. We like real-time rendering and solid geometry. This is basically the design of how I was trying to put the system together. You would have applications on the client, you'd have applications on the back end, mixed environments. You need to support local host testing, Amazon, whatever. We kept things simple with just using all REST as the APIs. So first, we need configuration. I need to be able to create these applications, the channels within them, define selectors, which I can get into a little bit later, but these are essentially a DSL to control how when jobs come into the system, they're then routed to different back ends. And then provisioning rules, which I'll also get into later, another set of DSLs for managing how you actually define your scalability profiles on the back end. So we need some kind of data service for this, and I use Zookeeper. So the coordination is sort of the back end system that deals with how are these workers, how are you controlling all the stuff on the background? How are you controlling your hypervisor? How are you doing all these things? And again, I had Debash's book here because it's the nature of Scala and the ability to write DSLs to expose these domain level semantics and these domain level languages is really, really important. So for example, in the provisioning, many workers can abide by what the CloudWatch API provides, but many can't, and you need a custom way of defining these kinds of things. The third service is fundamentally the compute services, which funnel work back into the workers and allow workers to then provide updates. So there's queuing system. We have certain requirements in terms of durability and message visibility, and there's lots of different versions of queues because we tie these back to costs. And so you might want something slow and variable and weird like SQS, or you might want something like very, very fast like 0MQ or even Zookeeper. And then finally, there's the front end, which is how work comes in. Submit, query, cancel, those kinds of things. And then setting up scheduling, job graphs, this sort of stuff. So this is the general service level design of the system. So I started back in, the beginning of last year with an early version of Akka and was overwhelmed by the amount of stuff I could do with it. And then, and Akka itself was kind of a kitchen sink at the time as well. And different iterations of the system used various, if not all of these things at one point. But over time, as my opinion is good architecture gets rewritten a lot and is simplified and things are thrown out. And so we've been able to do that quite a bit in Akka 1.0. does provide a lot of that. We removed a lot of the dependencies and streamlined the stuff, and also was able to understand the system better and the software better, so we were able to take advantage of that. Especially the ActorRef stuff that you had mentioned. It used to be that there was no ActorRef, so that you could basically modify, have mutable state on your actor interface. And then when we got away from that, it actually simplified a lot of things as well. So, again, how does Akka really help me? How did it help? I need to take an aside here and say that my initial task with this was to really just design a prototype and do a little bit of architecture around it. And my selfishness in using Scala was really just kind of happenstance. I wanted to learn something new. I bought a Scala book and a Clojure book, and I happened to read the Scala book first. And so it goes. And then I came across Akka and just really kind of looking for tools. And I didn't have any particular motivation behind using it, except that it was, it had a lot of stuff that I could just use right out of the box. But that said, it's a great, at least the kernel stuff is fantastic. And Akkers make it very simple to build highly concurrent systems, to build fault-tolerant systems, and then to distribute these systems. The community has been fantastic, and that's probably been one of the biggest reasons that I've continued to participate and continue to use the code. Jonas and Victor are just phenomenal. And the actor level stuff, the kernel stuff, we've never had a single issue as far as production goes. Other things we have, and I'll get to that in a minute. And then being able to use Scala directly it's been fantastic. And so it's been a real win, and there hasn't, with the exception of, if you heard all this talk in the morning, with the exception of the productivity gap and learning a new language. I mean, you could spend an entire day trying to figure out how to do it the right way in Scala, which you could have done in 5 minutes in Java or C++ or something like that. Okay, so this is a really basic list of some of the services, as I kind of mentioned in that other thing. Residents, I just kind of put this placeholder here for various things that just run regardless of what other service or whether their deployment are there. And that's typically connected to Zookeeper for doing machine level fitness checks, stuff like that. And then there's some actor pooling stuff. If any of you have seen Akka itself, we put this in also. So in a typical, your own build box, you just kind of run everything all at once. And this is typically controlled via the configuration file. It'd be interesting, to see how the remote stuff comes in because it's all the same file. When you want to start to put together remote development environments, say for your broader team testing, typically what I do is I take kind of the front end stuff, whatever my app servers are, just run 1 or 2 or however many numbers of those, and then I just kind of have the other services running on the other box. The interfaces are all just hidden behind CNAMEs. It's all REST. It makes it really nice and easy. Going into more of a staging integration kind of environment, typically still keep the app servers on the front end. Maybe they get bigger machines. Maybe there's more of them. But then I tend to split out the coordination and the configuration just to kind of understand how it might look a little bit more in production, especially since the coordinator is the one getting all the heartbeats stuff on the back end from the actual instances. And then in production, you can basically split these up however you like. And typically there's maybe lots of the first 2, although actually in practice they tend to just sit together as well because they scale pretty uniformly just by running them on the same box. So I mentioned the custom provisioning stuff before, and I want to make a little bit of note of this because what we do here is when you define your application and you define your workers, these are the things that run on all your AMIs. And so a worker connects and it deals with stuff. And as I mentioned, the CloudWatch is fine if you want to, if you have very good parity between the pressure that your application might put on the resources. It takes up all the memory, takes up all the all the packets, takes up all the CPU. But we got lots of cases with those fan-outs when this just doesn't apply, where we have workers that fan out other jobs, we have workers that interact with the other workers in like little local clusters, or that particular compute is just single-threaded, single core bound, and so we need a different way of being able to specify what we consider load and when to spin up or spin down additional workers. And so, so what we did is created a DSL for for codifying this, and I wish that Dibash's book had come out before I had to write this particular DSL. But basically what you do is you specify basically a program which allows, in a very general way, you to profile what you consider load. For example, in the case of all the cores, maybe a single worker would report back 50% load if 2 of the cores were being used, when it was doing its heart beating. You also set up configuration profiles for saying when you need to bring up new workers, where you want to put them, what are the AMIs, all the typical EC2 goodness. And this is all stored in Zookeeper. Then the channel coordinators, there's a channel for every channel, there's an actor running in the service which scans this stuff, which evaluates the need to be listening for these programs, and then it uses the HotSwap to essentially, it'll inflate one of these pieces of script, and it'll turn itself into an actor, and will inject that receive model, that receive partial function into that actor. And I'll actually show you a snippet of code. So this is one of those cases, it's not finite state machines, where changing the behavior of something that's running is actually incredibly important. So then the worker's sitting there heart beating, whatever the period is. He's sending, hey, I'm alive, hey, I'm alive, hey, I'm alive. But he can also send back like a custom script. And then what'll happen is, that will get run in basically every channel program has its own little sandbox. And so using the power of the parser combinator stuff in Scala, the workflow is essentially, hey, did you get something that routed to this actor? Run the script, run the program. If A is greater than B, then send a message to do something. And that do something is typically run, terminate, start, stop, something going on Amazon. And here's some code. So this is the channel coordinator guy. This evaluate rule thing is what he might get sent when Zookeeper was picked off and we find something, or a new channel was added on the fly. So that's the other great thing about Zookeeper is you can do all this configuration on the fly. The app never has to go down. This is not working. Oh, here we go. So this is an example of the trait which would have the receive method for getting this run rule, which would come from this post is handled from the heartbeat. And this little thing will match the script, and if this matches, well, when this thing is inflated, this guy becomes his own receive method, or the other one, depending on what message shows up. And this is where that run rule will get fired. So effectively what happens is your channel's configured, the thing spins up, it understands that there's a specific tag here, and when that worker starts to heartbeat back and send you update scripts, this will catch it and it'll get routed to the right place. It's all very cool. So I mentioned, let me get back to this for a second. So this post here, and I mentioned on some of the previous slides, this little thing called this mist. Everything, all the APIs were REST-based, and what I was running into problems was how to basically take these REST calls and make these, do all this cool asynchronous stuff, either without timing out or one of the other things. But one of the great pieces that, at least at the time, Akka provided was Atmosphere, which is this common thing. And it encapsulated your connection and a broadcaster and all the rest of it. But it was very, very hard to try to actually do this all the right way. And a lot of blocking calls and all the rest of this stuff. So you can't really see this, and you can read this later on. But basically, having this conversation with Victor about really trying to optimize this pipeline, because it just was not scaling with this REST front end and all this great cool stuff in the middle. And so Jonas had suggested at one point trying to treat this broadcaster as a future and all the rest of these things, and that was actually kind of going okay. But when you use a future, of course, you're blocking the thread that you're going to wait on. So things were happening on the back end okay, but under real stress testing, it was locking stuff up. So thinking about this for a while, I started to put a few things together, and the future approach was really nice. Using Jetty continuations was interesting. And how am I going to get rid of these timeouts? Well, I said, well, what would be the ideal thing to do? The ideal thing to do would be to have the HTTP request itself actually be a message. And that's what Mist was a way to try to get this into the active system as soon as possible. There's a little, some history here in terms of what I was experiencing that led to this conversation was some stuff happens, you go through Jersey or whatever it is, you set up a future because you think you're doing stuff great, but then you're hitting the database and you're coordinating all these other kinds of things, and you're dead. And then then you say, okay, well, let's try this future-based approach. Okay, well, that's pretty cool too. So some other stuff happens, it goes through your Pojo. Now you've wrapped up this broadcaster thing and you passed it along and you kind of modified your messages a little bit in order to deal with that, and it works. That's really cool. But my back end, I have the subscribe stuff going on. So people, all these workers are connecting, waiting for work, minimizing the amount of HTTP traffic in the background. Well, now I got to queue all this stuff up. I have to manage all these broadcasters and all these kind of things. Things time out. Got a lot of shared state now to distribute across all these machines. But it looked like it was going okay until it started to run AB and SOAP UI and all the rest of it. And my JVM died because Atmosphere, or my use of Atmosphere, was not bringing all the threads back down. And it was just killing me, and I just plain and simple couldn't use it. At that point, I kind of thought, well, I don't really want to dig into the code. I don't really want to figure out if it's, honestly, if it's my problem or their problem. I just need something else. So that's when I went with the MIST approach, which basically means, we'll start with Jetty and then later port it into Servlet 3.0. You customize your own dispatcher. So now it can run in its own thread pool. It can do its own dispatch on all these actors, separate from the kernel. You start the continuation and immediately turn it into an Akka message and then send it along. And now this is very, very cool because now you can just do bang, 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 and you get stuff that looks like this. Your get is just a message. I know there's a lot of conversation right now about making these all immutable, and I suppose from a language perspective that's the right thing to do, but I didn't really care. I have software to deliver. So I just exposed all the servlet stuff underneath. You want to get the request, you want to get the response, I'll give you plenty of rope, you do whatever you want with it. But now you have, complete with exception. In this case, I just take the message and I pass it along, single bang, go deal with the metadata. The thing is going to go talk to Mongo later on, and you're done. It's really, really cool. And so in this is another case where we use a closure to get rid of another double bang. So I've got this thing, I need to do some work. I really want to go update this, but I don't really want to wait until this code tells me that the data is updated in order to go return the response. So I just close it here with this. If it's all right, it's going to send a 200 back, and then I send it along here. Boom, Scala wins every time. So, and then this is what happens in my receive method. I get the message, I do my Mongo stuff, I call complete on my message. Now, the side effect of this is your messages have to get, you tend to break a little bit of isolation, or you have to do a little bit of wrapping, or they change a little bit, because now you've got to pass like HTTP requests along in your messages. Well, who cares? It's fast, and it works, and it's really awesome. And with that, the thread stayed completely flat. I was able to get like really, really good performance, and the servers, as I say, have not gone down since. So after that, Jonas and I had a conversation about actually putting that directly into Akka itself. We dropped Atmosphere. Again, I will attribute that mostly to my use of the stuff rather than Atmosphere itself. I think it does a great job for what it was designed to do. But because it was a corporate thing, we kind of had a little bit different way of going about it. So one of my big things inside Autodesk was to try to contribute more to open source. We signed the corporate CLA with Scalable Solutions. We contributed it to 1.0. We've done some other work around extending it for WebSockets. We've done some work about contributing actor pools and other kinds of things that we've written, mostly as a means to just kind of to give back into the community. And we also get a lot of great participation from the community, improving all the stuff that we fully intend to take back in. And we're looking forward to continuing the relationship, going forward. So overall, it's been a really good experience for me. I think there's been a lot of learning curve in terms of using this stuff and using the language and all the rest of it, but I've become a really big advocate of trying to build these systems, especially these internal distributed systems, using these tools. And so far so good, and I'm going to continue to use it in as many of the products as I have the authority to. So that's it. Thanks a lot. There's where you can pick that up. We're done.
There's a lot of documentation there.
Yep. Any questions?
Just dig in. We're releasing 101 next week, the first RC. One of those came out just before Christmas. Let us know what works, even more what doesn't work, so we can improve. Any questions so far? We have 4 minutes for questions. Yeah.
Can you talk a little bit about how it overlaps with other messaging frameworks that utilize, like the filter metaphor?
Yeah. That's a good question. How it overlaps with other messaging frameworks. One thing that the actor model, for example, that does not support is durable mailboxes, durable message queues. That is something that we actually have added to Akka, but it's not supported by most actor frameworks. So if you talk about the actor model generally it is what people also call send and pray. You send messages and they might get there and they might not get there. That is the guarantees that, for example, Erlang gives is very vague. And we are in Akka 1.101. We are actually adding things like idempotent receiver. We're adding guaranteed delivery. As I said, we also have a whole bunch of different kind of durable mailboxes backed by a journaling file-based transaction log, or even external systems. You can actually run it backed by ActiveMQ or AMQP, Rabbit, or so. It also doesn't have a lot of the bells and whistles that many of the other like messaging solutions have, like message selectors that you might have, and like a lot of abstractions for doing routing, like having AMQP. You have like you can bind to an exchange. You have a separation of queues and exchanges and stuff like that. But on the other hand, what it gives you is way higher throughput and lower latency. So it is a trade-off, right? If you need all the advanced messaging solution features, then you might need to go for that. But if you want to have a more lightweight, very highly performant solution with now even potential add-on for durability and guaranteed delivery, then it can be something you could look at. So and there's even more to say about that, but yeah, it is a wide topic, but it's a good question, because they can definitely be used to solve similar kind of problems, definitely. Yeah. Okay. Yeah.
How does the Akka STM compare to Clojur's STM?
Akka's STM is based on a library called Multiverse, and it all depends. I mean, if you talk about raw performance, I would say that according to the benchmarks that we've been doing recently with Multiverse 0.7, that is actually not released yet, you get much higher throughput with Multiverse. But that said, I mean, with micro benchmark, you can prove anything you want, right? So I don't want to say anything. I mean, CCSTM basically that is the basis for the Scala STM, and as well as the Clojure STM might be faster for specific use cases. But Peter Venture doing Multiverse has done a fantastic job of really writing a system that really performs well on Java. For example, at runtime he has 0 object allocations, so there's not a single object allocation whenever you run. So it's no GZ at all, and he's gone really far. If you look at the code, it's definitely not idiomatic Java code. It's very ugly. But it's just because he wants to get as much throughput as possible through the system. So you need to probably take your problem and bench it yourself. But Multiverse is fantastic technology, and I don't regret basing the Akka STM on top of that. So, yeah.
I was wondering about the beta launch of the Cloudy Akka project, and how that was going, and also how that related to the new rewrite of the forwarding actor.
Yeah. That's a good question. We are actually going to move. It's not really announced yet, and we haven't really exactly drawn the line yet. But a lot of the stuff that we announced in the cloudy Akka is actually going to go into the open source. We're going to draw the line at operations, that we said. So everything that is needed for operations, meaning monitoring, management, provisioning things, all that things that you want to dashboard and all that stuff through. This is going to be in the commercial version, but all the stuff that I showed you now, I mean replication, load balancing, distribution, all these things. I mean cluster membership, leader election, all these like hardcore distributed computer science problems is going to go into the open source version. It's going to go in Akka 2.0, which hopefully going to come in summer. So there's it's still being worked on, but all the things are there basically in APIs basically. I've done some blog posts, so you can see how you can do all these things, like replication and fault tolerance and other things on the cluster. But what we want to go into at this level of transparency. So it's only a configuration thing. It shouldn't be any APIs because then you lock yourself in. So that is what we're working on right now.